And again, how does water move relative to the contours? It's going to be moving perpendicular to the contour line. Alright, what problems are associated with groundwater pumping? This top image, we're looking at a healthy aquifer. This is before overpumping has occurred. And overpumping simply means you're drawing out more water than the system can naturally recharge. Okay, so before overpumping, the water table is fairly flat and water flows to the left past the small well. In the second image, larger wells, or just this one larger well, causes a cone of depression in the water table, changing the direction of the flow. Okay, so you can think of this like a milkshake. Okay, if you're drinking from a straw, drinking your milkshake, it's going to create a little cone of depression there. It's going to sink in around the straw because you're drawing it out faster than it can naturally flow back down to the bottom of the straw, or in this case, to the bottom of this larger well. So a cone of depression forms because water cannot flow fast enough to replenish the amount of water that is withdrawn from the well. In many cones, the water table becomes steeper near the well because water is drawn out too fast. And so it ends up, like I said, and like these arrows demonstrate, changing the direction of flow. Other problems of overpumping. As the water table drops, the aquifer compacts, causing subsidence of the land surface. Fissures form along boundaries between more and less subsidence. This is a big problem in the Phoenix area, especially in the outskirts where the suburbs rely primarily on groundwater. And Queen Creek has huge earth fissures and other areas, and Phoenix is experiencing subsidence, meaning the whole area is getting lower in elevation. It's sinking as a result of drawing the water out of the pore spaces below the ground. If you do this in a coastal or island environment, then you have a different set of problems. Fresh water floats on top of salt water because it's less dense, and so overpumping can draw salt water into the bottom of coastal wells, so that contaminates those wells. And areas can drop meters to tens of meters in elevation when we're talking about subsidence. It's a really big deal, and to detect subsidence, they do repeated surveying with conventional surveying equipment, GPS, and other satellite measurements to measure the surface and see what is its elevation and how is it changing over time. Once compaction occurs, the pore space cannot be regained if the water table is allowed to rise. So you lose permeability, you lose porosity, and the storage capacity of the reservoir is depleted because all of the pore spaces, that porosity you had before, that was all filled up with water, you draw the water out and it collapses. There's no way to, reinflate that, to get that pore space back. Once it's collapsed, it's gone. Fissures related to subsidence can be tens of meters wide, kilometers long, and tens to over 100 meters deep. Fissures provide easy access for contamination into groundwater without being filtered, and this is a big problem in Phoenix as well. If you ever go out to any of the fissures surrounding the Phoenix area, for some reason people love to dump their trash there, and I don't know what that's about, but it's the worst place you could possibly dispose of anything because it's like a direct route down to the water table. So if you're dumping, motor oil or anything like that becomes a contaminant, old batteries, whatever it is, cleaning supplies, that goes straight down into the groundwater and contaminates our water supply. This map shows elevations of the water table beneath an area. Which way does the upper level of groundwater flow? Generally toward the what? Remember, on these maps, north is up. Okay, if you said south, you would be correct. So again, what we want to do is look for the highest elevations and the lowest elevations, and we know it's going to be flowing from the highest to the lowest. So our highest ones are in the north, our lowest are in the south. So we know that groundwater is going to be generally flowing toward the south. This figure shows a new well that will pump out groundwater faster than it can be replaced. What will the water table look like after pumping? If you said D, you would be correct. This image we have here where the water table is lower surrounding the well, that's our cone of depression. And a cone of depression is just where we have drawn out groundwater faster than it can be replaced. So D is the answer here. B, if we take a look at that, where we've got a mound of groundwater under the well, that might be if we have a recharge well. So sometimes when you've been pumping groundwater, other wells will be used to recharge, to pump that water back in. And so you're going to build up water around the well because it cannot spread out as fast as it's being pumped in. A and C are not viable options for anything really, other than the water table is at a slope. What happens to the water table if groundwater is pumped out faster than it can be replaced? I'm going to zip right through this one because I just talked about it. This is a cone of depression. So a cone of depression forms on the water table when groundwater is pumped out faster than it can be replaced. All right, expanding on what we were just talking about with earth fissures. This is just an example to show the earth fissure that formed on Rogers Lake at Edwards Air Force Base in California, January 1991, and forced the closure of one of the space shuttle's alternate runways. It's a huge deal. The fissure has been attributed to land subsidence related to groundwater pumping in the Antelope Valley area. So if we take a look at this map here on the right, we're showing water level decline in feet. So the water table's dropping in all of these areas. In some areas more than 200 feet. And we have those areas right around us, clustered right around Phoenix. It's kind of scary to think about how little rainfall we get to recharge our aquifers naturally, and how much water we draw out so rapidly. So we do get fissures all over the place, and now that you're thinking about it, you'll be more aware. You'll see it in the news and things like that. Every now and then there's something on the news about a fissure popping up in somebody's yard or something like that. If this popped up under your house, that would be a huge deal. It would break your foundation and that sort of thing. So they can be quite serious. All right, what do you already know about water contamination? Okay, I'm sure have heard about water contamination on the news. Last year there was a big scare about pharmaceuticals in the water, the BP oil spill contaminating water. Anytime there's a disaster, something like Katrina or a big earthquake, there's usually water contamination issues. So you already know something about water contamination. You already know there are all sorts of things that are not okay to just go and dump in a river, right? So let's take a look at 10 ways water can become contaminated. Mining in naturally mineralized rock, meaning the process of mining requires all sorts of chemicals. A lot of times rocks have to be dissolved in acid to get to the actual material that you want in the rock. So those materials associated with mining can become contaminants, and sometimes what you're mining itself can be a contaminant. For example, if there's lead in the mine, lead poisoning is a very serious problem, and can contaminate the groundwater. The same thing goes for mercury or uranium. All sorts of things that we mine can also be a natural contaminant. Landfills. There are all sorts of things that we throw away that can end up becoming contaminants. And landfills are actually very interesting because they lay down layers of impermeable material in between each layer of trash. So what's interesting is they're blocking all oxygen and blocking all water from coming into the landfills these days, which is great as far as preventing contamination of groundwater. But what's so interesting to me is that they've really entombed the trash. So if there's no oxygen in there, there's no water in there, they're preserving it. It's like a big mummified landfill. It's really interesting, and it's no wonder that it takes so long for the things that we throw away to actually break down, because in a landfill, we have stopped the natural process of decay in the hopes that we won't contaminate our current situation. It's just interesting. Septic tanks. We live in the city, most of us, and so we don't have to deal with septic tanks because we have sewer systems, but it's very common for septic tanks to be leaky, and that is a horrible situation because then you have human waste, which can carry all sorts of disease, potentially contaminating the groundwater. The next is farms. Pesticides, herbicides, and fertilizers are huge groundwater contaminants, and can really mess up both the groundwater and the surface water, because so many chemicals are now used on farms to prevent pests, to prevent weeds, to enhance growth, that all of those chemicals get into the river and then affect the growth of whatever is in the river. It's really interesting and kind of scary, really, that is the case with conventional farming. Lots of potential contamination there. Leaking tanks in gas stations have been a major culprit in the past for groundwater contamination. It's better now. In the 90s, there was a huge crackdown on leaking underground storage tanks, and so a lot of gas stations went out of business just sort of overnight, because suddenly the regulations said that whoever is contaminating is responsible for the cleanup, and the cleanup of these types of leaks can be extremely expensive. Truck fuel spills. So depending on what the truck is carrying, whatever type of material is there, if they get in an accident, they're spilling whatever they're carrying, whether it's, toxic waste or, something that on its own in a small amount would be benign, but in a large quantity can cause massive problems. As well as the diesel fuel that is fueling the trucks. So big trucks in any sort of rollover accident is a really big potential contaminant. One you probably don't think about is the dry cleaners. Okay, how do you get your clothes clean without water? How do you wash something without it getting wet? They use a chemical process, and for years those very hazardous chemicals were just getting dumped right into the ground. They don't get dumped in that way anymore, but they still are using the same very hazardous chemicals and are still a big contributor to groundwater and surface water contamination. So think twice before you buy that garment that requires dry cleaning. Households. Our households contain all sorts of things that you wouldn't want to drink, right? Anything you would hide from your toddler or from your pets because you don't want them getting into it is a perfect example of a contaminant. So whether it is prescription drugs or bleach or detergents or things for your car, anything like that, batteries, old technology, laptops, computers, things like that, when they are improperly disposed of, can lead to contamination. And so be careful about what you put down your drain. It's not just what you spill on the ground or send to the dump, but if you put something hazardous down your drain, that's working its way into our water system. Brought in by the river, so if there's a river flowing through an area that is contaminated, it's just going to continue carrying that contamination downstream. In the same way, it can be brought in from outside areas through groundwater. So just like the river is flowing downhill, groundwater is flowing downhill. So if uphill from your community there is a polluting factory or someone who's, I don't know, dumping bleach on the ground, something awful, that can work its way down the groundwater table. Factory wells, spills, and emissions. And this is another, it seems like a no-brainer, but up until not too long ago, big factories were still able to dump their waste in wells on their property. That is not the case anymore. They can get fined for that sort of thing by the EPA, but the contamination still exists. And the same thing happens with runoff. So if they have hazardous materials on any surfaces and it rains and it runs off, that's going to get into the groundwater as well. That's what we have here in Phoenix from the airport and from Luke Air Force Base. All of these solvents used to clean off the airplanes and make them safe for flight end up working their way into the groundwater and causing what are called Superfund sites, which are large areas of contamination. We have several of them here in the valley. Fuel storage tanks. This is similar to the leaking tank in the gas station, but on a larger scale and above ground. So it's actually easier to fix because you don't have to dig it out of the ground, but if there is a leak and it's on this larger scale, that can cause a problem. How does groundwater contamination move? So the example we have here is a house with a septic tank. Contamination largely moves with groundwater down the slope of the water table. It can be naturally filtered out with enough time. It flows slowly and in contact with material like sand. If it's not filtered, it flows rapidly through a rock such as limestone with open cavities. Okay, so that's the example on the right here with the tilted white layers is flowing rapidly through cavities in a limestone. And so this is not filtered on the right. On the left, it is filtered slowly through something like sand. It's important to consider the direction of groundwater flow when citing the relative positions of a well and contamination sources, such as a septic tank. In general, put the well uphill of a septic tank, but be aware of what is farther up the hill. Okay, so even if this guy on the right with the leaky septic tank and water that's flowing slowly, he decides to put his well uphill, depending on how quickly that tank from the house on the left has its contamination flowing, his water well might get contaminated as well. Okay, so how does contaminated groundwater move? It moves with the groundwater down the water table, and it's either filtered slowly through something like sand, or it's not filtered and it flows rapidly like in limestone. How do we track and remediate groundwater contamination? Contamination spreads out due to diffusion and mixing, forming what we call a contamination plume, which is just a big body of contaminated water. On a contoured water table, we can see the concentration of the contaminant and track the plume. Okay, so we want to, this is a step here. On the first image, we know, okay, we see we've got contamination, now what? The first thing we want to do is draw contours on the water table, figure out what direction the water's flowing, and draw out our contamination plume. Then we want to drill wells to intercept the plume, and we pump out the water and treat it. Depending on what the contaminant is, we're going to treat it in different ways. Okay, so pump out the water and treat it. And then the last step is to dispose of the contaminated water or treat it with activated charcoal or certain geologic materials. So again, depending on what type of contaminant it is, it's going to have a different treatment. Sometimes you just have to dispose of the water, and sometimes you can clean it up and pump it back into that system. Where do we get our water from in the United States? So describe where the U.S. gets its water. Okay, in the upper left corner here, we see how the U.S. gets their fresh water, and this is from 1990. So we get 259 billion gallons per day from surface water, things like lakes, rivers, streams, springs, that kind of thing. And 79 billion gallons per day come from groundwater. Okay, that's where we get our water from. 79 billion comes from groundwater, and 259 billion comes from surface water. Describe how the United States uses its water. Okay, so we've got a couple different images here that you can use to figure out how the U.S. Uses its water. On the upper right, we've got it broken down by groundwater versus surface water for each of the main uses. 137 billion gallons per day goes to irrigation. 38 billion gallons per day goes to public supply. 4.9 billion gallons goes to mining. And 4.5 billion gallons goes to livestock. Okay, if we break it down further, the uses of fresh water in the United States in 1990, in the bottom left-hand corner, we've got this chart. We see 50% of the fresh surface water in the U.S. gets used to generate power. Again, this is something to consider when you are using electricity around your house, because this is something you have control over. When you use less electricity, not only are you saving money on your electricity bill, but you're contributing less to your carbon footprint because of the fossil fuels that are used to generate that power, and you're also saving water, which is so important here in the desert. 33% of our fresh water in the U.S. goes toward irrigation. And it may seem like that's something that can't change, because this is a huge chunk, and irrigation is important, right? We need our crops. But what can be improved is what crops are growing where. Arizona used to be known for all sorts of different commodities that started with C, right? We had copper, cotton, cattle, and citrus. So you don't wander around the desert and naturally find citrus trees or cotton fields or cattle roaming naturally, right? These are all things that have been imported into a desert environment, and now because they cannot grow here naturally, we have to pump water out of the ground to create this artificial environment to provide water where there is no water, and grow crops that would normally grow in humid areas here in the desert, right? So there could be better planning going on. We can grow the drier crops here and leave things like cotton and citrus for more humid environments like Florida and the southeast. 9% in this graph is going to public use, 6% to industry, less than 1% domestic, less than 1% commercial, and less than 1% livestock. So again, as I mentioned at the beginning of last week's lecture, when we were going over water use, part of this 33% irrigation is growing crops for livestock to eat. This less than 1% for livestock does not include what they are consuming. It only includes what water they drink. Okay, how is water consumption changing? So we can take a look at this graph in the bottom right-hand corner here and see how it's changed over time. So starting in 1950, we have 150 billion gallons per day of surface water being used. Okay, we compare that to 1980, where it peaked around 350, and then it's declined down to 1990, just above 300. So if we look at how groundwater is being used, it was at about 25 billion gallons per day in 1950, and it peaked in 1975 around 75 billion gallons per day, and it stayed right around that level. That level is on the rise these days as we have less and less surface water available, and communities in arid climates like our own continue to grow, and the demand for water increases. We're relying more heavily on groundwater because that's what we have access to for now in desert environments. This map shows contours of the water table, the location of 4 factories labeled A, B, C, and D, and contaminated and uncontaminated wells. Which way will the contamination flow? Okay, so everywhere you see an X is a contaminated well. Everywhere you see a dash is a non-contaminated well. Our factories are labeled A, B, C, and D. So you want to take a look at the contours and figure out, according to these elevations, what direction would the water flow? If you said south and southwest down the contours, you would be correct. So let's take a look and see why. Number 1, north and northeast up the contours. Okay, that means the water would be flowing uphill, which never happens. this is completely impossible. Water does not flow uphill. It only flows downhill. Number 3, northwest and southeast parallel to the contours. Okay, if the water is moving parallel to the contours, that means instead of flowing down a hill, the water is wrapping around a hill because it's moving along the contours. And that's physically impossible as well, so we know it can't be 3. And number 4, impossible to tell because the movement of contamination is independent of groundwater. Okay, that's false. We know that contamination moves with the groundwater. So it has to be south and southwest down the contours, because to the south and the southwest the elevation is getting lower. So it's going to flow towards the lower numbers. The map shows contours of the water table and the location of a factory that contaminated groundwater. Where would you drill wells to intercept the contamination? If you said number 3, southeast of the factory, you would be correct.